hello everyone. In this video, we are going to solve problems in chapter 4 about first law of thermodynamics. So here's our problem. A cylinder is initially filled with saturated liquid water at a specified pressure. The water is heated electrically as it is steered by a paddle wheel at constant pressure. The voltage of the current source is to be determined and the process is to be shown on a PV diagram. So note that the cylinder here is stationary and thus the kinetic and potential energy changes are zero. So this cylinder is well insulated and the heat transfer is negligible. So the process here is a quasi-equilibrium in both compression or expansion. So first law of thermodynamics states that the energy that comes in minus the energy that comes out is equals to the change in energy of the system. So electrical work that comes in plus work of the paddle wheel minus the work output is equals to the change in internal energy. So since kinetic energy and potential energy is equals to zero, then the electrical work that comes in plus work of the paddle wheel is equals to the mass times the change in enthalpy. So we have here the pressure 1, which is equals to 175 kilopascal in the saturated liquid table. Then our enthalpy, specific enthalpy of liquid at 175 kilopascal is equals to 487.01 kilojoules per kilogram. So by the way, since our internal energy plus work output is equals to change in enthalpy during a constant pressure quasi-equilibrium process, so the properties of water are found in table A-4 through table A-6. So we are now in the specific volume. So specific volume of the saturated liquid at 175 kilopascal is equals to 0.001057 cubic meter per kilogram, and our pressure 2 is equals to 175 kilopascal since it is a constant pressure process. Then we have here the x sub 2 is equals to 0.5. So our enthalpy at state 2 is just equals to specific enthalpy of saturated liquid plus x sub 2 multiplied to the specific enthalpy of saturated liquid vapor mixture. So by substituting the values, so 487.01 plus the quantity of 0.5 times 2213.1. So our specific enthalpy at state 2 is 1593.6 kilojoules per kilogram. To get for the mass, we have here the formula, which is denoted by mass is equals to volume over specific volume. So we have here the value of 0.005 cubic meter over 0.001057 cubic meter per kilogram. So cubic meter here will be cancelled, so we are left with the mass, which is equals to 4.731 kilogram. So to get for the volts, we will first solve for volts over change of time plus
400 kilojoules. So it is equals to the mass, which is 4.731 kilogram, multiply to the change of enthalpy, which is 159.3.6 minus 487.01 enthalpy at state 1. Then the unit is kilojoules per kilogram. So kilogram will be cancelled out. Then we are left with, so the answer is 4835 kilojoules. So now we have to solve for the volts. So volts is equals to 4835 kilojoules over 8 amperes multiply to 45 times 60 seconds is the change of time. Then conversion factor of 1000 volts ampere over is equals to 1 kilojoule per seconds. So ampere here will be cancelled, kilojoules per second. So the volts required is equals to 223.9 volts. So the figure in our PV diagram would look like this. So here is our state 1 going to state 2 at constant pressure.